This will be part 2 of our topic review of irreducibility of polynomials, where I will show you some examples that will illustrate how to apply some of these theorems that we talked about in part 1. Of course, you have done these examples already, some of them in the homework, but this is just to remind you how to apply these theorems again. And I suggest when I actually write a polynomial and tell you what to do with it, that you pause the video and try to do it yourself before you actually watch how I do it. All right, so let's start with the first problem. Number 1, factor into irreducible factors the following polynomial, f of x equal to x squared plus 2x minus 5. It's a polynomial with coefficients in Q. And I ask you to do this over Q, R, and C. Okay, you can pause the video now and try to do it yourself. And I will now show you how to solve this. Okay, so because we are asked to do irreducibility over C, we know that we will need to compute the roots. And in any case, it's a degree 2 polynomial, so we know that the polynomial of degree 2 is irreducible if and only if it has no roots in a given field. So the roots will be useful anyway. And to solve this polynomial for roots, so roots of f, we can just use the quadratic formula. So what are they? They are minus 2 plus or minus the square root of 2 squared minus 4ac, so plus 20 divided by 2. So that gives us minus 2 plus or minus the square root of 24 over 2. So I can factor out 4 from here. So I get 1 minus 1 plus or minus square root of 6. And I see that this does not belong to Q, but that this element does belong to the reals and to the complex numbers. Why doesn't it belong to Q? Because if it did, then 1 is also a rational number, and Q is a field, so I can add these two. I can add 1 and minus 1 plus radical 6, and if I do that, then I get radical 6. So if this number here is a rational number, then that means that radical 6 is rational, and we know it's not. And in fact, in the next lecture, I sort of developed this topic to discuss much more generality, which nth roots of various rationals are actually rational and which aren't. But in this case, let's just take it on faith that radical 6 is not rational, and then it follows that minus 1 plus or minus radical 6 is also not rational. Okay, so having this, I know that a degree 2 polynomial is irreducible if and only if it has no roots, so I have an answer that tells me that f is irreducible over Q, and f factors as x minus 1 plus radical 6 and x minus 1 minus radical 6. So this is the factorization of f over Rn over C. Why is it the factorization over Rn over C? Well, first of all, the factors, right, have to live in the correct rings of polynomials. Note, the coefficients of this polynomial are 1, the coefficient at x, and then this number is the constant coefficient. Here again 1, and this number is the constant coefficient. So both 1 and these constant coefficients are actually real numbers. So we get that these factors live inside Rx. They also, of course, live in Cx. And secondly, both factors are degree 1. So are irreducible. Right, so this is factorization of f over R and C into irreducibles. All right, let's do another example. 2. Same question. For f equal to x squared plus x plus 1, another polynomial with coefficients in q. And again, I ask you to pause the video and try to factor this polynomial into irreducibles over q, r, and c. And now I will show you how to do this. So there actually, so there are two methods to do this here. So the standard method would be this. It's again a quadratic polynomial, so I find its roots. And the roots of f are, so it's -1, again, quadratic formula, plus or minus radical -3 over 2. I see these roots do not lie in the real numbers, so they also do not lie in q. And of course, they do lie in c. So I get that f is irreducible over q and over r, and f factors as x minus -1 plus radical -3 over 2 times x minus -1 minus radical -3. So this is the factorization over c. Why is f irreducible over q and r? Because it's quadratic and has no roots in q or r. These two factors have coefficients in c, and they're both degree 1, so they're irreducible. Okay, an alternative method to solving this problem is the following. For once, note that this is a polynomial of the form, so f of x is equal to x to the p minus 1 plus x to the p minus 2 plus 1 for p equal to 3. And 3 is prime. So by the last theorem we stated towards the end of our previous video, we know that this is actually irreducible. So f is irreducible over q. What about over c? Well, you can either now use this factorization over c, or you can actually also see it in a slightly different way. Namely, also note that if I take this polynomial f of x and I multiply it by x minus 1, this is the f of x, right? X squared plus x plus 1 times x minus 1, what do I get? If you do the multiplication, you get x cubed minus 3. So what does that tell me? This tells me that the roots of this polynomial are actually cube roots of unity. And I know that there are 3 cube roots of unity. One of them is 1, and then there's zeta 3 and zeta 3 squared. And because 1 is not a root of this, the roots of unity, which are the roots of f, are actually the zeta 3 and zeta 3 squared. So f of x factors in this way. Where zeta 3 is cosine 2 pi over 3 plus I sine 2 pi over 3. So this gives you something curious here. This, of course, this factorization must be exactly the same as this factorization, because we have uniqueness of factorization in polynomial rings over fields, which means, one of these roots is actually zeta 3 and the other one is zeta 3 squared. I give it to you to figure out which of them is which, right? Use a picture on a complex plane to figure out which root is which. And I see, of course, I know the cube roots of unity other than 1 are not real. So this must be the factorization over c, while f must be irreducible over r. Yeah, so as zeta 3 squared do not belong to the real numbers, f is irreducible overall. Okay, so any of these methods, these two methods gives you an answer for this question. So let's move on to another example. Three x to the fourth plus 4x squared minus 6. It is again a polynomial with rational coefficients. And again, I suggest you pause the video now and try to factor it into irreducible factors over C, R, and Q by yourself. And let me now show you how to do this. So it's a quartic polynomial, degree 4, but it's really a quadratic in disguise. It's something that we call biquadratic. So you can use substitution, u equals x squared, and then this reduces to u squared plus 4u minus 6, and you get the roots in u, let's call them u1, u2, which are minus 4, again I'm using quadratic formula, plus or minus the square root of, so that's going to be 16 plus 6 times 4 over 2, so that's minus 4 plus or minus the square root of 40 divided by 2. I can factor out 4 from here, so that will leave me with minus 2 plus or minus the 4 gives me the 2 after I factor it outside of the radical and cancels with that 2, so it's plus or minus radical 10. Yeah, 4 over 2 gives you the 2 here, and then this becomes 2 radical 10. Again, I see that this is not in Q, but let's not worry about this for the moment. So how do I get the roots of f? So roots of f, well, just essentially by substituting each of these two values for u, you solve this little equation for x. So you get plus or minus the square root of minus 2 plus or minus radical 10. Sorry, that's just plus or minus radical 10. All right, so you have 4 roots in total, 4 complex roots in total anyway. So I immediately have the factorization over C. Is this f of x is equal to x minus the square root of minus 2 plus radical 10, x minus the square root of minus 2 minus radical 10, x plus the square root of minus 2 plus radical 10, and x plus the square root of minus 2 minus radical 10. All right, each of the factors has coefficients in C, and each of them is of degree 1, so they're automatically irreducible. There's, of course, factorization into irreducibles. I'm not going to keep writing this. This is what we're doing here anyway. What about the reals then? Okay, I look at the roots, and I want to see which of them are real roots. The important thing here is that radical 10 is greater than 2. In fact, greater than or equal is only what I care about, but it's actually greater. So note. Which means this thing is positive. Oh, this thing is definitely negative. This thing is positive, and this thing is negative, right? This is just a repeat. And you know that the square root of a positive number is real and the square root of negative number is not real. So that means I have that f of x, I can definitely collect the real factors. That's this one. And then that one is also real. Well, these two do not live inside the constant terms do not live inside the real numbers. But if I multiply them together, I get x squared minus, so it's actually going to be plus, right? Let me write it like this. It's minus 2 minus radical 10, which is, of course, the same thing as x squared plus 2 plus radical 10. Okay, and so I claim this is a factorization over R. Clearly, note this bit has coefficients in R, this also, and so does this, right? Because radical 10 is a real number. These are irreducible over R because they are degree 1, this and that. Irreducible over R as they are degree 1, while this one, this one does not have degree 1. However, it has degree 2, and I know it has no roots in R because I know exactly what the roots of this polynomial are. They're these two non-real roots. So reducible over R as of degree 2 and no roots in R. Okay, let's do yet another example. So example 4. But this time the question is going to be slightly different. Oh, sorry, there's also factorization over Q. So is this polynomial irreducible or does it factor over Q? You note that you can actually apply the Eisenstein criterion here with the prime 2. Now, 4 is divisible by 2, as is 6, but 2 squared does not divide 6. Okay, it divides 4, but that's not important. The important thing in the Eisenstein criterion is that the square of the prime does not divide 6. So we get that f is irreducible over Q by the Eisenstein criterion as 2 divides 4, 2 divides 6, but 2 squared does not divide 6. Okay, I'm not going to write it, but the other important thing is that f is monic, has rational coefficients that are actually integers. Okay, so 2 more examples. Example 4 is the following polynomial, but a slightly different question. So, is f of x, which is x cubed minus 6x plus 18, irreducible over Q or C? Okay, you can again pause the video and try to answer this question. And now let me tell you the answer. So over Q, f is irreducible by the Eisenstein criterion. as, okay, what primes can I use? There are two primes that divide the coefficients, 2 and 3. Note that I cannot use 3 because 3 divides 6, but 3 squared also divides 18. But I can use 2. As 2 divides 6, 2 divides 18, but 2 squared does not divide 18. Over C, f is reducible because the only irreducible polynomials over C are the degree 1 polynomials. So the last question is, what about the real numbers? And here we can use a trick from calculus. Namely, if I could show that this polynomial has a root in the real numbers, then I would know it's reducible. Because its degree is greater than 1, and it has a root, so it must have a linear factor. So the other complementary factor will have degree 2, so it will also be a non-unit. So over R, note that if I take the limit as x goes to minus infinity of f of x, I get minus infinity. And when I go with x to infinity, I get plus infinity, right? The graph of the polynomial looks like that, or maybe like that, I'm not entirely sure. But definitely as I go to negative infinity with x, it goes down. When I go to positive infinity with x, it goes up. So, as f is continuous, its graph must cross the x-axis. Hence, f has a root in R, so is reducible. Over R. Now, if you ask me to factor it into irreducible factors over the reals or the complex numbers, that's a difficult problem because it's a cubic polynomial, and there is something called the cubic formula, but it's actually quite complicated. But the irreducibility actually in this case can be settled in an easier way. All right, and finally, the last question is this. Factor into irreducibles over Q and C. Note, I'm not asking about the real numbers. The polynomial f of x equal to x to the 7 minus 1. Again, I encourage you to pause the video and try to do this yourself. Okay, so how do we do this? You quickly notice, right, that the roots of this polynomial are 7th roots of unity. All the 7th roots of unity. So over C, that's how it factors. The first root of unity is x minus 1, then I have x minus zeta 7, x minus zeta 7 squared, x minus zeta 7 cubed, x minus zeta 7 to the 4th, x minus zeta 7 to the 5th, x minus zeta 7 to the 6th. Well, zeta 7, right, is cosine 2 pi over 7 plus I sine 2 pi over 7. So this is the factorization into irreducibles. Over C, again, all the coefficients are complex numbers, and they're all the factors are degree 1, so they are automatically irreducible. What about over Q? Now, this polynomial definitely has a root over Q, namely 1. So I know it's not irreducible over Q. And if I factor this polynomial, I mean, if I factor out the x minus 1, you can either do long division, do x to the 7 minus 1 divided by x minus 1, and then you'll get the other factor. Or you can just notice it's always the same pattern, that the other factor is going to be this. Now this is irreducible. As the degree is 1. What about this? Now this is one of these polynomials for which we proved irreducibility, or we didn't prove it in the last video, we proved it in class using this clever application of the Eisenstein criterion. But towards the end of last video, we stated that all the polynomials that look like x to the prime minus 1 plus x to the same prime minus 2 and so on are irreducible over q. What's the prime here? The prime p here would be 7. This is x to the p minus 1. When p is 7, this is x to the p minus 1, x to the p minus 2, and so on. So this is irreducible also over q. So last theorem in the previous video. Okay, this completes our review of irreducibility of polynomials.